Hi everyone, welcome back. In this particular video, we're going to look at another method of synthesizing alcohols. And we're going to introduce a new class of reagents called Grignard reagents. So we'll talk about what these are, why do we need these and how do they operate, what sort of benefit or advantage do they offer. So let's quickly review what do we know about alcohol synthesis. And we're going to focus on synthesis of alcohols from carbonyl compounds. Okay, so focusing on the synthesis of alcohols from carbonyl compounds. Now, what we've seen previously is that if you have a carbonyl compound, these can be converted into alcohols using two hydride reagents. We also learned about the hydrogenation, but I'm going to focus on the hydride reagents. So you could use sodium borohydride, not putting down all the conditions here, but you could use sodium borohydride or lithium aluminum hydride for converting a carbonyl compound into an alcohol. Now, if you look at the details, if I start with an aldehyde, by doing this, by using one of these methods, okay, so the aldehyde is converted into a primary alcohol. Okay, that's a primary alcohol. If we start with a ketone, and using either one of these methods, a ketone, which is another carbonyl compound, right? This is converted into a secondary alcohol. Now, you cannot make tertiary alcohols by using this method. So aldehydes would be converted into primary alcohols. Ketones would be converted into secondary alcohols. You cannot make tertiary alcohols here. So the question is, are we limited then, right? Is this all we can do? Can I only convert an aldehyde into a primary alcohol and a ketone into a secondary alcohol? Or is it possible for us to convert an aldehyde into a secondary alcohol and maybe a ketone into a tertiary alcohol? Is that possible? Okay, let's see what would that take. Okay. So if we think about it, when we have an aldehyde, and if I want to convert this into a secondary alcohol, okay, that is a secondary alcohol. This is an aldehyde. And this is a secondary alcohol. To do this transformation, looks like we need to bring in an R group. We have to bring in an alkyl group, a carbon-containing group. How do we bring it in? And again, to think about it, okay, let's actually go think about what happens in the sodium borohydride reaction, for example. So when we had the aldehyde, and when the aldehyde was converted into the primary alcohol, I'm going to draw in some detail, include some detail here. Okay, when we did this reaction can be alcohol, aldehyde, going to a primary alcohol. We used sodium borohydride, or this is one of the reagents that could be used. And hydride is the source of a nucleophilic hydride, because what we know mechanistically, what happens mechanistically is that the hydride goes and attacks this carbonyl carbon, which is electrophilic in nature. It has a del positive charge to it. And that's how we end up with this primary alcohol, where we have two hydrogens connected to that carbon, which was previously the carbonyl carbon. Because note that this carbon is that carbon, the alpha carbon in some sense, okay? So that's your alpha carbon in the alcohol. Okay, so a hydride, which is a H with a negative charge on it, comes and attacks that carbonyl carbon and gives us the primary alcohol. Now, if you use the same logic, go to the previous example here. We want to convert an aldehyde into a secondary alcohol. And when I do sort of an assessment, of what changed, this carbon here, the alpha carbon, which is the carbonyl carbon here, okay, looks like this has the hydrogen on it, which was already here. That hydrogen is here. And what we've added is an R group. And based on this mechanism, it seems like we need to bring in an R, this R prime, as a negatively charged group. Okay, because if this R prime has a negative charge on it, then that negative charge can come and attack that carbonyl carbon, very similar to the hydride. And then using a similar mechanism, right, this carbonyl, the double bond O would open up and then it would get protonated, you would get the secondary alcohol. So now the question is, okay, how do we get an R prime or an R group which has a negative charge on it? Now, by an R group, remember we're talking about maybe something like CH3 with a negative charge, or it could be an ethyl group, CH2CH3 with a negative charge, or it could be a phenyl group like a benzene ring with a negative charge. We want a carbon with a negative charge on it. And the big question is, have we seen so far, have we seen a carbon with a negative charge on it? And if we haven't, why didn't we? Okay, so think about all the functional groups or all the compounds that we've met so far, that we've been introduced to so far. We've learned about alkyl halides. That's one functional group. We are talking about alcohols. We know carbonyl compounds, right? These are some functional groups that we are already aware of. And if you look at the carbon here, which is connected to the halogen or connected to the oxygen or connected to the oxygen here, this carbon is always electrophilic. It has a del positive charge on it, or it might give us an intermediate with a positive charge to it. Why is that so? It's not because of the carbon itself. It is because of what's connected to the carbon, okay? This carbon here is partially positive because it's connected to a chlorine, which is partial negative, or which is more electronegative than the carbon. Here, the carbon is connected to an oxygen, which is more electronegative than that carbon itself. Here again, the carbon is connected to the oxygen, which is more electronegative than the carbon itself. So it's not the carbon per se which decides whether it's going to have a positive charge or a negative charge. It seems like it's the other element that it is connected to. That's what dictates the charge. Okay, so with that thought in mind, if we want a carbon or an R group with a negative charge, we would want it to be next to or be in contact with something, be bonded with something that's less electronegative than carbon, sorry, okay, or more electropositive than carbon. And an example of such reagents is where this R group is next to a metal like magnesium, being a classic example. Now, in this particular case, the magnesium is positive, and so the carbon gets a negative charge. And reagents like these are called Grignard reagents, okay? So Grignard reagents these are of the form or of the type R. There is some carbon containing group which is bonding with a magnesium with, I'm putting Br there, it doesn't have to be Br, magnesium with a halogen. The X is usually chlorine or bromine. Iodine is also a possibility, fluorine is not so much, okay, okay, so that's the case. And in this particular case, the R is a negative charge and the magnesium is positive. So a Grignard reagent is a source of carbon nucleophiles. It's a source of carbon nucleophiles, carbon with a negative charge. And these are synthesized from alkyl halides. Okay, so essentially what we can do is if you have an alkyl halide, you can react this alkyl halide with metal, magnesium metal, and the solvent that's typically used is THF or diethyl ether. Okay, THF or ether. When you do this, you get the Grignard reagent, RMGX. So in this case, the magnesium here, okay, the magnesium is a divalent metal. So the magnesium is 2+, and so it is bonding, or it is bonded with the X, the halogen, which brings in one negative charge, and the R, which brings in one negative charge. That's how it becomes neutralized. And so the Grignard reagent serves as a source of a nucleophilic carbon, as a source of R-. And by doing this now, okay, by using the Grignard reagent, what we can do is, using Grignard reagents, aldehydes can be converted into secondary alcohols. Ketones can be converted into tertiary alcohols, and a specific aldehyde, formaldehyde, which is the smallest aldehyde possible. It's a 1-carbon aldehyde, formaldehyde. Okay. This aldehyde, formaldehyde, it can be converted into primary alcohols. Okay. So aldehydes are converted into secondary alcohols, ketones are converted into tertiary alcohols, and formaldehyde is converted into primary alcohols. Okay, now Grignard reagents, these are very strong nucleophiles, and these are also strong bases and are pyrophoric. Okay. That means, again, these react with water violently. Okay, it can result in a fire. Okay, these actually are pyrophoric. We can say hygroscopic. All of those. Okay, so these can like react violently with water and cause fire actually, depending on the Grignard reagent. Not all Grignard reagents, but some Grignard reagents can actually do that, and they're very hygroscopic. So any manipulation using a Grignard reagent must again be done in the absence of water, very similar to lithium aluminum hydride. Okay, so let's look at some examples here, details of how Grignard reagents can be used. And we look at the general mechanism, and then we will look at an example for each of these transformations. So the general reaction for using Grignard reagents, if I were to write a general reaction, would look like this. You have a carbonyl compound. You react this with a Grignard reagent. I'm going to use R prime MgBr with, let's say, THF. That's your solvent. And second, you have to again quench this reaction with some workup, acidic workup. And when you do this, your product is going to be a tertiary alcohol. So the R prime from the Grignard reagent, that carbon-containing group gets connected to the carbonyl carbon. Mechanistically, what happens is you have your R prime MgBr. This is negative, this is positive. So the carbon nucleophile goes and attacks the carbonyl carbon. That double bond opens up. It brings me to an alkoxide. And this is the first step. In the second step, this alkoxide reacts with acid, okay, gets protonated using the acid, which is the workup here. And so that way we get the alcohol. So you get the tertiary alcohol in this particular case because we're starting with a ketone. Okay, so this is a ketone. So our product is going to be a tertiary alcohol. Let's look at a specific example. So let's say if I started with carbonyl compound like this is a ketone, and we react this with let's say methyl magnesium bromide 1 using THF as a solvent, and 2 H3O plus. If we did this, our product is going to be that tertiary alcohol. Okay, that would be our product, because again, mechanistically, what's happening is we have our methyl magnesium bromide. This comes and attacks the carbonyl carbon. The C double bond opens up. This is step 1. And this would give us the alkoxide. And then when we do the acidic workup, the alkoxide gets protonated to give us the tertiary alcohol. So ketone goes to tertiary alcohol. Okay, that would be the reaction here. Now, similarly, if we start from an aldehyde, reagent here, or we have an aldehyde as a starting material along with the Grignard reagent. Okay, if we start with an aldehyde and we react this with, let's say, propyl magnesium bromide. The only issue here is that this is an ionic bond, so it is best shown like this. Okay, it's not a covalent bond, so there are 3 carbons here with a negative charge to it. So let's say if we react with propyl magnesium bromide in THF, follow it with an acidic workup, our product here is going to be that alcohol. Okay, and plus this alcohol is going to form as a racemic mixture. This is an aldehyde, and this is a secondary alcohol. Now, why did I bring in the racemic mixture here? Because we are generating a chiral carbon over there, a chiral center there. Okay? So if you follow it mechanistically again, we have propyl magnesium bromide. Okay, 1, 2, 3 carbons. And we have 1, 2, 3 carbons here. So we're bringing in 3 additional carbons in principle. Okay, so that carbon goes and attacks the carbonyl carbon, opens up. And this is the first step. And so we're going to get an alkoxide where we have 3 additional carbons now. We have 1, 2, 3, and then 4, 5, and 6. So we brought in 3 more carbons. That will be our alkoxide. And realize that this carbon here, the carbonyl carbon, it has always been sp2 hybridized. It is trigonal planar. That means the attack of this Grignard reagent, very similar to the hydride reagents in lithium aluminum hydride, sodium borohydride, very similar to that. The attack can happen from both faces of that carbonyl carbon, right? Because the carbonyl carbon is a flat species. So now the Grignard can come and attack from the front, or it could come and attack from the back. So depending on, and both of those attacks are equally likely. And so it's going to generate a racemic mixture for you. So this alkoxide here is going to be a racemic mixture. And again, by a racemic mixture, what I mean is that we have 2 molecules here. One is going to be one where this group came and attacked from the front because there is a hydrogen over here. And the second is where that group came and attacked from the back. because the hydrogen is now on the wedge. So you could show it that, or you could put the oxygen on the wedge or the dash. Either ways is fine, as long as you're showing two enantiomers here. Okay, so those are the two possibilities here. And then in the second step here, this is getting protonated. So the oxygen is going to get protonated, and that will give you the secondary alcohol. So that's how you make the secondary alcohol starting from an aldehyde. An aldehyde is always going to give you a secondary alcohol as a product. And finally, to make primary alcohols, you start from formaldehyde. Okay, so if I start with formaldehyde, and if I react this with a Grignard reagent, so let's say ethyl magnesium bromide, and let's use diethyl ether as a solvent. That's another polar aprotic solvent, which is can be dried, can be obtained in an anhydrous form. So if we use the diethyl ether, follow it with an acidic workup, we're going to get a primary alcohol. Okay, so we have two carbons here, we have one carbon here, so we get a 1, 2, 3 carbon alcohol. Okay, so mechanistically again, it's the same throughout. So we have the ethyl magnesium bromide minus plus goes and attacks that carbon, opens it up. Okay, brings us to an alkoxide. Now the ethyl group is 2 carbons, so it will bring us to an alkoxide here, because that's the third carbon. So we have 2 carbons here and 1 carbon here, 3 carbons total. So 1, 2, 3 carbons, and then the O minus, because it's that carbon. I don't know if it helps to write it a different way. We can write it like this so that you can see the connection between formaldehyde and this alkoxide. So this is where the ethyl group is connected. Okay, the ethyl group got connected to that carbon. And then in the second step, we have the workup. Comes in, picks up that proton, and that would finally give me that alcohol, which is basically an ethyl with a CH2 and an OH. That's what we're looking at here, ethyl with a CH2 and an OH, so we get that product. Okay, so that's the chemistry of Grignard reagents. Again, the interesting thing about these Grignard reagents is that they serve as a source of carbon nucleophiles. We're going to be using them throughout other chapters in organic chemistry too, or other sections of organic chemistry. Okay, so with carbonyl compounds, they help us to make alcohols. They convert carbonyl compounds into alcohols, but they also add more carbon atoms. Okay, that's one key. So when you synthesize alcohols using Grignard reagents, you can add carbon atoms. You can add carbon atoms, okay, when you're making these alcohols. I hope that helps. Have a good one. Bye.